for this opportunity to come to this wonderful place, although it's a little bit cold. So I am the last person between the program and the lunch. I'll try to be brief. So today I would like to talk about studying the Kondo lattice physics using Moiré superlattices. So this is not a machine learning project. This is still postdoc graduate student learning project. But if machine learning can help us to tune the knobs to the appropriate regions of the phase diagram, we would be very much appreciated. So now it comes down, of course, to collaborators and the people who did the real job. Professor Kim-Fan Mak is in the audience. This project was led by former postdoc Wenjing Zhao, who a few days ago joined University of Delaware as an assistant professor, former grad student Zui Tao, and current graduate student Yi Qi, and postdoc Dong Dong, who is on the job market. So excellent postdoc if you have faculty opening. We got HBN Crystal from, again, this NIMS group. So, you know, the Kondo effect is very old, almost 100 years old. You know, it tells about this very unusual scattering problem of a conduction electron in a metal with magnetic impurities. And this Kondo lattice problem studies the interaction of conduction electron with a lattice of local magnetic moments. Again, as I said, you know, this is an old problem. It's a prototype, strongly correlated system. It's simple enough, but still captures a lot of very interesting physical phenomena. It's pretty good model for you know, high TC superconductor or heavy fermion materials, and it predicts very rich phase diagrams, you know, including magnetic and non-magnetic, superconducting, and you know, heavy fermion physics. So in the one limit, you know, when the F electrons, which is the localized spin system, hybridize strongly with the conduction electron, the Fermi surface gets enlarged because the F electrons contributed to the latitude volume of the electron Fermi surface C. And then that also gives the quasi-particles strong mass because of the narrow band of the F electrons. On the other hand, when the electron-electron, well, spin-spin interaction is very strong in this case, you get small and a light Fermi surface. I jumped ahead myself too much. I should have introduced the system a little bit more. I assume you know, but let me just remind you the parameters in the problem. So we have a conduction electron, and we also have a localized magnetic moments. You can have a hopping for the conduction electron, and a conduction electron interact with the localized magnetic moments through Kondo effect, this JK. And then, of course, you can have Heisenberg interaction between the localized spins. That's the JH. So we're looking at the interplay between those two magnetic interactions, and when we tune this axis. And then in between those interesting phases, you know, you can have quantum productility and a non-Fermi liquid behavior. And often also you can observe superconductivity. So conventionally, the bulk heavy fermion materials are made of crystals containing, you know, 4F or 5F electrons. listed here. And then if you look at their electronic band structure, pretty much like a spaghetti. And, you know, the simple model I showed in picture in the last slide captures something like very flat bands, you know, due to those electrons and some conduction bands. So this is a very complicated system. Furthermore, the bulk crystals are relatively hard to control or tune compared to 2D systems, which I'm going to talk about. Often in order to change, for example, the density of conducting electrons or the Kondo coupling, other effects, you need to substitutionally doping this. So you need to grow, you know, different crystals in order to get one point in your phase diagram. So the idea here is that, you know, why don't we use the tunability of the Moray materials, you know, Long advertised quite a lot in his talk to mimic a Kondo lattice problem. So the building material I'm going to talk about in my talk, Liang has already introduced it. It's a transition metal dialkylcarbonide semiconductors. And the way you can just think about it, it's some kind of a gapped graphene. And the interesting physics happens at a K and a K prime point. So you have two values. So the gap here is about 1 to 2 electron volts. One kind of important property I would like to point out is that, you know, all the Moray physics, you know, we are talking about K or K prime electrons. And if you look at their, you know, electronic band structure, they are time reversal copies of each other. So if you look at just the one value, it breaks time reversal symmetry. So that means the hopping is a complex. And this has a very important consequence. Okay, so what Moray does is to introduce a longer length scale and a different energy scale. So because kinetic energy and a Coulomb interaction energy scales with the length differently, we can increase the ratio of the interaction energy and the kinetic energy by making the period larger. So for Moray period on the order of 10 nanometers, typically we can get this ratio to be bigger than 1, which will make the interaction effect important. Or in the band picture, you can just think about applying new periods, you know, much bigger than the atomic period, and that will fold your bands, and you're just looking at the tip of your bands, and that will make the band flat. And the same language is saying, you know, electron-electron interaction is important. So some earlier theoretical work already projected this problem to interaction Hamiltonian. So in the case when you have a single Moray band decoupled from the rest, then you can think about this problem as some kind of a Hubbard model, you know, very strong on-site Coulomb, and then you can also include the longer range Coulomb interaction, and then the hopping term. And if you have 2 bands and you can introduce some complex hopping between the two, somehow when the conditions are right, you can also make those bands topological. So and that's something Liang talked about. So first, let's just focus on this. Okay. So if we have a very flat band and you half-fill it, for example, the strong interaction can open gap, and this becomes a Mott insulator. So when electrons form a Mott insulating state, the charge degree of freedom is frozen, and what's left is just the spin degree of freedom. And this gives us a platform of lattice of, you know, spin of magnetic moments. So this is one of the important ingredients to build this Kondo lattice using the Moray superlattice. Okay, here is some early experiments from our group and also from other groups as well that shows that half-filled first Maury band can give you marked insulating states. So this is resistance measurements, at the filling equal to 1, that 1 particle per Maury unit cell because of the double, spin valley degeneracy. This is a half-filled band. We get resistance increases when we cool sample down. So this is an insulating state. On the other hand, we can measure magnetic susceptibility, and the magnetic susceptibility increases when we cool down the sample, and it follows this Curie-Weiss law, at least for the high temperature part. And this Curie-Weiss temperature gives us the order of magnitude estimate for the exchange interaction. And for this particular example, it's 1 Kelvin, and it's negative. That tells us, it's antiferromagnetic interaction. And this parameter can be tuned by changing the ratio of T and U in the experiment. So now we have a lattice of localized spin. And in this particular case, because of the threefold symmetry of the system, we have a triangular lattice, and you have, localized spin on a frustrated lattice. Okay, so now we have 1 ingredient. So the next ingredient is to bring in a conduction electron. So imagine that you have 2 layers. 1 layer has a very strong Maury potential, and then you can put the filling into 1 particle per Maury unit cell, and that forms my insulator. So we have a localized moments, a lattice of it. Now you can have another layer, which is kind of coupled to this blue layer, but in this red layer, we have a weak Maury potential. So in that case, you can modify the band a little bit, but not too much. So those electrons can still be itinerant. So then combining the two will have a Kondo lattice. Okay. And then the Kondo exchange is determined by hopping between the 2 layers and the energy difference, in this case, this is the lower and this is the higher Hubbard band. And this is the distance between this dispersive band and the one of the Hubbard bands. So the Kondo exchange goes like a 1 over that energy scale. So by looking at this, you say, when one of them is small, then my Kondo exchange is strong. But when those both are kind of big, when this band in the middle of the 2 lower and Hubbard bands, this Kondo exchange is the weakest. Okay. And then the Heisenberg exchange, determined by hopping in this strong Maury lattice layer, and also mediated by the conduction bands through the RKKY. And then those parameters can be tuned by electrostatic gates. We can, shift the alignment of those bands, and then we can also shift the Fermi level doping. Okay. So this is my outline and also the main message in case, you want to take a little bit break before lunch. I hope I will be able to convince you that we realize a tunable triangular Kondo lattice using this Maury bilayer. It's not specific for this system. You can come up with other Maury system to achieve this. we can break down the condo singlets by applying magnetic field. You can also break down the condo singlets by reducing conduction electron density. I'm not going to talk about this. You can find out more in this publication. And my main point here is that I hope I can show you that near the condo breakdown induced by magnetic field, there's a new phase which has bad metallic bulk properties, but chiral edge state. And we coin this, state as term metal. So I hope I will be able to convince you about this. Okay, so the pair we picked is this multi-telluride tungsten selenide moray. And this is the STM image of this. One of the reasons we picked this pair is because moray is formed mainly due to the lattice mismatch between the two materials. And because of that, we have a relatively small moray inhomogeneity because the lattice period mostly is just, because of the lattice mismatch. And the period is about an order of magnitude larger than the atomic lattice. So on the order of 5 nanometer in this case. And you can see the triangular moray lattice. You can also see this honeycomb formed by high symmetry points. So in fact, in this system, if you look at the lowest moray bands, the electrons or holes, I should say, in multi-telluride occupy, one triangular lattice, and then the tungsten occupy the other. So together we form a honeycomb lattice. But one triangle living in one layer, the other is the other. Okay. And then it turns out that, because of this tungsten selenide layer actually has a weaker moray potential, and a multi-telluride has stronger moray potential. I can get into details if I'm interested why. But this is what we verified experimentally. And some of the parameters I just listed here, so the highest valence band actually is the multi-telluride, and then the tungsten selenide, the highest valence band is about 200 millieV below. But we can change the potential difference between the two layers by applying a vertical displacement field. Then you can shift the band alignment below, and then gradually you can also make them at the same level, even above. So the bandwidth of a tungsten is much wider, and this, gives you, because of the weak moray, the mod state of this is about 30 millieV, and that gives us some room to tune. Okay, so let me just show you some experiments. Well, before I show the data, let me just guide you through, the phase diagram, which we'll be looking at again and again. So this axis is the filling factor, which shifted the Fermi energy. And this axis is the displacement field, which changed the potential difference between the two layers. For small displacement fields, if you dope it, charge goes to the multi-telluride layer because that's the highest valence band. And if we do like a filling above 2, then for a little bit of big displacement field, you can push the tungsten band sort of a little bit above. So you first fill the multi-telluride, and then you start filling the tungsten selenide band. So this is like a band gap, and that will serve as our kind of test, control experiment. But if you increase the displacement field more, you can push the tungsten band even further up. And then for filling equal to 1, we can put the multi-telluride into the Mach insulating state for charge transfer. So if you add a little bit more, then the charge will go to the tungsten selenide link. So in this case, we do have the system I described. The molybdenite is inside the MAR gap, and the charge will continuously fill the tungsten selenide. And then if you increase the field further, you can invert the two bands, see interesting topological properties as well. So let me just show you some experiments. So here's the experimental setup. So we have this moray, and we have top and the bottom gates. So the two voltages can tune the total hole density in the bilayer and also the interlayer potential difference, which I show as electrical field independently. And this is on the high magnetic field. And you can see low resistance stripes, and those are Landau levels. And everywhere when you see, and the tungsten selenide has a higher mobility. So, when you look at the Landau level of the tungsten selenide, you see very high contrast stripes. So everywhere you see this vertical stripes, so that means, the displacement field does not change the filling of the Landau levels. So that just means, it's not shifting charge from one layer to another layer, right? So you can read out from here that, within this area, charge actually is only inside the tungsten selenide layer, and the top molybdenite is in the MAR gap. And this is filling 1 plus X, and this is 2 plus X. And interestingly, if you push the displacement even higher, you see this zero resistance state. And if you look at RXY, you get quantized. So this actually is a Chern insulator, and this persists down to zero magnetic field. So this is a quantum anomaly Hall insulator. And that happens at much higher displacement field. So we'll be focusing on this region number 2. That's the corner lattice region. So from this picture, we immediately see that the MAR gap survives even when you dope charge, into the bilayer, when the tungsten selenide is hole doped. So that's kind of one important ingredient. And we can also look at the mass of holes in the tungsten selenide layer. If it's really dispersive, then we expect the mass to be similar to the monolayer case. And indeed, this is the case. We measure the whole mass using the quantum oscillation on the magnetic field, and it's pretty much comparable to the monolayer case. So we have two ingredients, survival of MAR gap in molybdenite when tungsten layer is hole doped, and nearly itinerary hole mass in the tungsten layer. So we do have a corner lattice now. Okay, so now we can look at the transport. This is just a control experiment, when one moly band is fully filled and charge just goes to the tungsten band. You see the reasonably good T-square at low temperature, the Fermi liquids. And as a comparison, if you look at the other case, with doping 1 plus X, at low temperature, still some kind of a square dependence, but there's a bump. And then, this characteristic temperature is dependent on doping density of the conduction layer. And if you look at the coefficient, this A coefficient, in this case, this guy is very different compared to the other case. So what's happening here is that below this T star, the coherent transport develops, and this can be described by Fermi liquids, but with different mass. And you can compare the mass, so the 1 plus X effectively be much higher. Really? Okay, I need to jump. So get you to lunch. Okay. So what I'm trying to say that masses become heavier, and then if you look at the Fermi surface, this low magnetic field, you have a large Fermi surface, and then at the large magnetic field, you have a small Fermi surface, and there's a jump in the unit of the Murray unit cell. And what's happening here is that magnetic field breaks down the Kondo singlets, and that causes the density change. So what's kind of interesting I want to show actually today is this interesting phase, in this Kondo lattice regime. If we look at the magnetic field dependence, you see that for low magnetic fields, there is no Landau levels, and above Landau levels emerge, and this is because we have Kondo breakdown. So now you can just think of the two layers kind of decoupled, and the tungsten has high mobility, Landau levels show up. But below this, we have this blob, and this blob has very small resistance RXX, but large RXY, and it's as large as 26 kilo. Okay, and then if you look at the magnetic dispersion, it's not linear, and also much higher slope than this Landau level, so not turn equal to 1, 2, or anything. Okay. So what is this? So we have a Kondo breakdown. We have heavy Fermi liquids before breakdown, and the light Fermi liquids above this magnetic field. Somewhere here, there's something interesting. So what is this phase? Let's look at the entire phase diagram. So this is when you apply very large magnetic fields, you decouple the two layers. And at the low fields, actually we see this arc. Okay. And this is because, as I mentioned, right in the middle, the Kondo coupling constant is the smallest. And that's why, you get, this kind of shape. If you look at the state here and state here, this is state we know it's a quantum anomalous Hall. You get a quantized RXY, but somewhere here, close to be quantized, but not strictly quantized. And RXX is finite instead of a 0. And the temperature scale also a little bit different. This is about 1 Kelvin, and that's about 2 Kelvin. This state is compressible from the compressibility measurements, and you can do a test to show that indeed this is real chiral edge state by doing current-induced breakdown, and this mimics the quantum anomalous Hall and quantum Hall breakdown induced by current. And you can also do non-local transport, and we find that this state behaves between current insulating state and the normal metal, and this is fully consistent with Landau-Buttiger simulation. So I think I'm running out of time. So the question is, where do you get this chiral property? And so Andy Millis and the collaborators point out in this paper that chiral exchange, Kondo exchange, and interlayer hopping actually takes the factor form, takes this p-wave chiral form, and I think this is due to the k electron. So basically, due to Kondo coupling, and some of these properties actually being predicted. It's between, this heavy fermion and a metallic chiral spin liquid in frustrated lattice. So I don't have time to explain this. So let me just put up the phase diagram. So this new phase, chiral metal with chiral edge state and pretty bad metallic state in the bulk occurs near Kondo breakdown, very much near this. That's the phase space. And it's different from doped chon insulator because that's in very different phase space. And I'll just stop here. Okay. Sorry.
And let me take the chance. So for Muco one, the charge transfer insulator, so does the ferromagnetic region fully overlap with the chain insulator region, or the ferromagnetic region is wider? For Muco one, this.
Say that again.
Okay, so the Muco one can charge transfer insulator. So I'm wondering whether the ferromagnetic region fully overlap with the chain insulator region, or the ferromagnetic region is wider, so to say.
No. So this only lives here.
Okay.
That's the only phase space near the Kondo breakdown.
Okay. I'm wondering about
Yeah.
Muco one, just at the initial feeling. So Muco one for.
No. So this is not. This is.
Okay.
That's what you're.
Yeah. I can come on later. So yeah, Long, yeah, please.
Just to clarify, phenomenologically, you see a compressible metal state and there is some coexistence of chiral, but these two things are different, right? I mean, what gives you churn is not the metal.
Okay. So so you may ask the question. No, so this is the metallic state.
Yes.
Okay, and it has an edge, chiral edge channel. That's what I mean.
Yeah, but it could be like two, I can think of the system have two parts. One is, basically on top of the churn insulator, I have another small pocket of some charge.
So what you are talking about is doped chon insulator, right? So this is a very conventional way to get this chon metal, but what we observe here is very different from what you are thinking about, the doped chon insulator.
No,
So-
I'm not talking about dope. You have a churn insulator and you dope the bands that's involved in the churn insulator. I'm talking about the additional trivial pocket.
Yeah, that's what you're talking about.
That's what I'm talking about.
Yeah. So this is very different because it has very specific, it has, this is the all, Yeah, so we can talk more.
Yeah,
at lunch.
let's talk at the lunch. Okay, so great. So let's thank you again for very nice talk. We have the beef and the chicken and also vegetarian lunch box. Please take it. And then we are back at like 12 or 45 for Sammy Mitchell's kind of lunch talk.